This video I'm going to show you how to answer questions on upper and lower bounds. So before we look at some examples, just going to explain to you briefly what upper and lower bounds are all about. Well, this is an extension of the rounding topic. In fact, it's a reversal of the rounding topic. Now, when we have answers that are rounding, usually we have to give it to a certain degree of accuracy. So, for example, in my picture here, I've got the number 32, and that is to the nearest centimetre. Now that tells me that my answer that I had got must lie between the values of 31.5 and 32.5, because any value in between those two numbers, if I rounded it, would give me the answer of 32. So these numbers here, this 32.5 and this 31.5, are what we call the lower bound and what we call the upper bound. So this first question, we are told that 350 has been rounded to the nearest 10 and we need to calculate the upper and lower bounds. Well, the technique for finding this is actually quite simple. All you do is start off with your value, so in this case it was 350. And now I'm looking at the value it's been rounded to, and this is the nearest 10. So all I'm going to do is write 10 bigger and 10 smaller than my original value. Now the upper and lower bounds are actually going to be the values in between these. So my lower bound would be 345. My upper bound would be 355. Now how do we display our answers? Well, usually they ask you to display your answers using inequality notation. So how do we do this? Well, we start off by putting an x in between because this is our unknown number. And we need to show that x is greater than 345, so we use an inequality sign here. And we need to show that x is smaller than 355, so we use a similar inequality symbol there. Now, if you remember back to your rounding rules, if our value was 5, then the number rounded up. So we need to make sure that we also include this lower value, because if we had 345 and that was rounded, that would round to 350. But we're not going to put a line under the other one because 355 would actually round up to 360, so that stays as it is. Okay, so let's look at the second question. This time we have 5 meters rounded to the nearest meter. So that means I need to start off by going up 1 meter and down 1 meter. And again, my values of the upper and lower bounds are going to be the values in between. So that is going to be 4.5, 5.5. And using the inequality notation, I'm going to have the symbol with the line under it there, and just the simple inequality symbol there. We can even use this technique for values that have been rounded to 1 decimal place. So in this case, I've got the number 5.6. Now, if I wanted to increase by 1 the value in the first decimal place, I would end up with 5.7. And if I wanted to decrease it by 1, then I would get 5.5. Now again, looking at the values in between, I end up with 5.55 and 5.65. And again, I want to use my inequality notation like that. We can even use this for numbers that are rounded to significant figures. So again, I would start off with 6.73, going up by 1 in the third significant figure place. Now remember, the third significant figure place is this value here. It's the third number counting from the left. And so increasing by 1, we would get 6.74, and decreasing by 1 would be 6.72. Again, want to go in between those two values, which is 6.725 and 6.735. And again, I need to use my inequality signs to show that. Okay, so here's 4 questions for you to have a little practice with. Pause the video, have a go at them, and then we'll run through the answers in a little bit. Okay, so this first question, we had the value 2,400 and we were asked to round to the nearest 100. So we needed to go up 100 and down 100, and then our upper and lower bounds were the values in between. So that was 2,350, 2,450, and using the inequality notation, your answer should look a little bit like that. The next question was a little bit trickier. I hope it didn't catch anybody out, but the first value was in meters, whereas I was told that this was rounded to the nearest 5 centimeters. There's a couple of different ways of doing this. I think the easiest way is just to convert this value here into centimeters, and 0.8 meters is 80 centimeters. So I start with 80 centimeters. I need to go up by 5 centimeters and down by 5 centimeters. And then my upper and lower bounds are going to be the values in between, which is 77.5 centimeters and 82.5 centimeters as well. And so these values again use your inequality notation. Now at the same time you could have kept it in meters and you would have ended up with 0.775 meters and 0.825 meters. That would also be the right answer. It just means that you've just done it in meters instead. So the next question was practicing one decimal place. So we start with 7.9. Going up by 1 decimal, we end up with 8. And going down by 1 was 7.8. So finding the values in between, we get 7.85 and 7.95. Again, use the inequality notation. And lastly, we've got this value, which is 8.92, and this was rounded to 4 significant figures. So again, this is a bit of a tricky one because this looks like it has been rounded to 3 significant figures. We've only got the 3 numbers there. So actually what we've got here is the number 8.920. So then if we go up by 1 value, it's 8.921 and 8.919, and the values in between are going to be 8.9195 and 8.9205. Okay, so now we know how to find upper and lower bounds of values. We're going to look at what happens when we have to calculate with upper and lower bounds. Okay, so here I've got 2 values. Firstly, I've got A, which is the number 60, but that has been rounded to the nearest 10. And I've got the number B, which is 400, but this is rounded to the nearest 100. So I'm going to start off by finding the upper and lower bounds of A and B. Now, you can use the technique that I've shown you in the past, but after you've used it a couple of times, you might find that you spot a pattern. You can do this really quickly. So I'm going to do it without the technique, and I know that the upper and lower bound of 60 rounded to the nearest 10 is going to be 55 for my lower bound and 65 for my upper bound. And likewise for B, the upper and lower bound is going to be 450 for the upper bound and 350 for the lower bound. Okay, so now we're asked to find the upper and lower bounds of A plus B. Now the big misconception here is to just do the sum. So in this case, A plus B will be 60 plus 400, which is 460, and then find the upper and lower bounds of this. Okay, so to the nearest 10, this is going to be 455, and then we've also got 465. Now I'm just going to keep this here, although I'm just going to highlight again that this is completely wrong, and you don't want to be doing this, just to show you why it's wrong in a moment. Okay, so actually what we need to do is we need to be using the bounds we've just calculated. Okay, so these are the bounds for A and also the bounds for B. Okay, so we just need to think a little bit about what would be most appropriate here. And obviously to find the lower bound, okay, I'm going to add the 2 lower bounds together. So that's 55 and 350. Okay, and this is going to be the value of A plus B. And my upper bound, I'm going to add the 2 upper bounds together, which is 65 plus 450. Makes sense, doesn't it? The 2 smaller numbers added would give us the smallest possible answer, and the 2 biggest numbers added together would give us the biggest possible answer. So here, if I add the smallest values, I get an answer of 405. And if I add the 2 bigger values, I get the answer of 515. Okay, so let's go back to our original sum, the one that I said was wrong. If we compare the lower bound here that we've just calculated and the lower bound that we calculated earlier, you can see that it is significantly better when we use the bounds first. And exactly the same thing with the upper bound. If we compare the 2 upper bound value, so the upper bound we calculated here, is significantly bigger than the one we did here. So I'm just going to highlight again that this is the wrong way of doing it. Do not do the sum first. We need to do the bounds first and then use them to get the lower and upper bounds. In the second question, again, we've got a little trap that a lot of people fall into. So I'm just going to highlight this first. Now, when doing B minus A, the thing that most people do, and it makes a lot of sense, is, well, to find the biggest value, the upper bound, I'm going to take the upper bound of B, and I'm going to take away the upper bound of A. And likewise, if I want to find the lower bound, surely I'm going to take the lower bound of B and take away the lower bound of A. And doing this really quickly, I get the values of 385 and 295. Okay, but again, watch out because this is wrong. And I'll show you why now. In fact, to get the smallest value when taking away, what I really want to do is I want to start off with the smallest possible value, which is 350 for B. And then I want to take away the biggest possible value of A because I want to take away as much as I can. So in this case, I've done the smallest value of B, but I've taken away the biggest value of A. And it's likewise over here. If I wanted to get the biggest possible value, I'm going to start with the biggest possible value of B, but I only want to take away the smallest value of A. So in this case, I get the smaller value of 285, and I get a larger value of 395. So again, quickly comparing, you can see that this value here is still smaller than this value I've got up here. And again, comparing the upper bounds, this value here is larger than this value here. So again, this is completely wrong. Okay, so let's look what happens when we times and divide. Well, firstly, timesing is going to have the same sort of properties as adding. Remember to make sure that we don't times the values then find the bounds. We find the bounds, then times them. So here I'm going to get the lower bound by doing 55 times 350. And to get the upper bound, I'm going to do 65 times 450. So my answers are going to be 19,250 and 29,250. So timesing has the same sort of technique to it that adding does. Now when it comes to dividing, okay, this time it's going to be very similar to the takeaway. So again, I want to start off with the lower bound having the smallest possible value and then dividing by the biggest possible value of A. And likewise for the upper bound, I want to start off with the biggest possible value and then divide by the smallest possible value of A. Now again, my answer, and this time I'm going to get recurring decimals, so I'm going to have to round. I get a lower bound of 5.38 rounded to 3 significant figures and a value of 8.18 rounded to 3 significant figures. So again, just to recap, remember that firstly, if you're calculating with bounds, make sure you work out the bounds first. Then secondly, if you're adding or timesing, it's just straightforward. The upper bound, you use the upper and upper bound, and the lower bound, you use the lower and lower bound. But watch out when you're taking away or dividing. For the lower bound, start with the lower bound, but take away or divide by the upper bound. And then if you want to find the upper bound of either taking away or dividing, you want to start with the uppermost bound and take away or divide by the lowest possible number, the lower bound. Okay, so all of this is summed up in this table here. So it's a good one to just have to hand whenever you're doing any calculations. And hopefully with a little bit of practice or just a little bit of thought, you can work these sorts of things out for yourself. Okay, so here's 4 questions for you to have a quick practice at. Again, pause the video and then we'll run through the answers in a moment. Okay, so hopefully you've had a go at that. Again, let's start off by putting the bounds of A and B down. So 100 rounded to the nearest 10 is going to have a lower bound of 95 and an upper bound of 105. And for B, this time it's rounded to 2 significant figures. I'm going to have a lower bound of 5.15 and an upper bound of 5.25. Okay, so looking at the calculations, in order to get A plus B, Okay, for the lower bound, I need to do the lower bound of A plus the lower bound of B, which is going to give me a value of 100.15. For the upper bound, I need to add the upper bound of A to the upper bound of B, which gives me a value of 110.25. Okay, so for the takeaway one, remember this is the one we've got to be careful at. The lower bound, I need to start off with the lowest possible value of B, which is 5.15, and I'm taking away the biggest possible value of A, which is 105, which gives me an answer of minus 99.85. My upper bound, though, I need to start with the biggest possible value of B, which is 5.25, and take away the smallest possible value of A, which is 95. And this would give me an answer of minus 89.75. In the next question, I'm doing times. I'm doing A times B. Okay, in this case, again, it's just like addition. The lower bound, I'm going to do 95 times the 5.15, the two lower bounds multiplied together. And this gives me a value of 489.25. Then my upper bound, I need to multiply the two upper bounds, which is 105 times 5.25. This gives me a value of 551.25. And finally, division. So remember, this is going to be just like takeaway. So I'm going to start with the lower bound, starting with the smallest possible value of B, which is 5.15. I'm going to divide that by the biggest possible value of A, which is 105. And this, then rounded to three significant figures, is 0.0490. And now my upper bound, I'm going to start with the biggest possible value of B, which is 5.25, divide it by my smallest possible value of A, which is 95, and I get an answer again rounded to three significant figures of 0.0553. Okay, so in this next section, we're going to look at a couple of worded exam style questions. Okay, so there's no real new content here. It's just a case of reading the question really carefully, understanding what the question's asking for, and then applying what we've just learnt about bounds to answer them. Okay, so pause the video, okay, have a go at these questions, and then we'll run through the answers in a moment. Right, so this first question here, I'm told that a rectangular field has lengths 36 meters to the nearest meter and 22 meters to the nearest meter. Calculate the largest possible area of the field. Well, in this case, remember, if you're trying to find area, we need to times values together. Now, this time it's telling us just to find the largest possible. So we're looking for the upper bound of the area. So we start with the upper bound of the two lengths. So the upper bound of the first length, 36 meters to the nearest meter, is 36.5 meters. And then the upper bound of the second length is 22.5 meters. So to find the upper bound of both of these, I just need to times them. And I get an answer of 821.25 meters squared. In the second question, not only do we have to use bounds, we've got to use a little bit of reasoning as well. So well, firstly in this question, we're going to work out the bounds of Graham's speed. And we know this is a bounds question because it mentions the fact that this speed has been rounded. So this is the telltale sign of it being a bounds question. So we're going to start off because we know that he's traveling at 20 meters per second to the nearest 5 meters per second by raising it up by 5 and then making it smaller by 5. And then finding the limits, which is 17.5 and 22.5. And this is his speed, so we'll call it S. And using the inequality notation, we have the upper and lower bounds here. Now this is measured in meters per second, and unfortunately our time here, he needs to make the journey in 20 minutes, so it's not consistent in terms of time, and he has to make a distance of 16 kilometers, so we're not consistent with the distance either. So what we need to do here is change this unit of speed into kilometers per minute. So firstly, to change meters per second into meters per minute, I'm going to times by 60 because there's 60 seconds in a minute. So this firstly gives me a lower bound value of 1050 meters per minute. And it gives me an upper bound value of 1350 meters per minute. So this is meters per minute here. Next, I need to change the meters into kilometers, and to do this, I'm going to divide by 1,000. So in this first case, I get 1.05 kilometers per minute, and for my upper bound, I get 1.35 kilometers per minute. So these are kilometers per minute. Okay, so now I've done this, I'm going to use my compound measures formula. So remember this, it's quite useful to draw out your little formula triangle. And we know that linking speed, distance, and time together, we know that speed equals distance divided by time. So we're asked whether he'll make it in time. So if we calculate the time here by doing distance divided by speed, we can see whether it is above or below 20. Okay, so in this case, we want to find the upper bound of the time. We want to find the longest possible time he could take, because if that is less than 20 minutes, then he's definitely going to make it in time. So first off, we're starting with 16, which is not being rounded at all, so I can just use 16. And I'm going to divide it by the lowest possible value, which is 1.05. And when working this out, I get an answer of 15 minutes, rounded to the nearest minute. So not only will he make it in time, but he'll also have 5 minutes extra. So just to finish this off, we need to write a little sentence. Graham will make it in time. Okay, so this last example I'm going to go through is a typical type of question on the exam that catches most students out. So again, if you want to, you can pause the video, okay, but don't worry if you're not too sure how to answer this. I will go through it in a moment. Okay, so firstly, reading this question really carefully, I can see I've got a right angle triangle with two smaller lengths of 5.23 meters and 8.72 meters, both measured to the nearest centimeter. And I'm asked to calculate the size of the hypotenuse, giving my answer to an appropriate degree of accuracy. Now, this is the bit that actually throws people mainly. It's when it says giving your answer to an appropriate degree of accuracy. So what we're going to do is answer the question, and then I'm going to explain what this means in a moment. Okay, well, hopefully by now you will have spotted this measured to the nearest centimeter part of the question, which is telling me that it's a bounds question. And also this addition of a right angle triangle with two smaller sides is also showing you that it's a Pythagoras question. So just to help us really, we're going to draw out our right angle triangle, and we're going to put our two lengths on here, which I'm going to call A and B. Now let's say that A is this 5.23 meters. Now we know that this is measured to the nearest centimeter, so I'm just going to change these values to centimeters. So I know that 5.23 meters is the same thing as 523 centimeters, and this is what we're going to call A. And we also know that B, which is 8.72 meters, is the same thing as 872 centimeters. So to the nearest centimeter, we've got the upper and lower bounds of these. So A, okay, I've got 523 centimeters to the nearest centimeter is 522.5, and the upper one is 523.5. For B, exactly the same thing. The upper and lower bounds are going to be 871.5 and 872.5. Now, reminding ourselves of Pythagoras' theorem, in order to find the value C here, which is the hypotenuse, I need to square my two lengths and square root. So that is what my value of C is here. Now remember that squaring is timesing, so in order to get the upper bound here, all I need to do is square the two upper bounds, add them, and then square root that answer. And likewise for the lower bound, I'm going to square the lower bounds, add them, and then square root. So this value C here, the lower bound, like we said, is the square root of the two lower bounds squared and added, so that's 522.5 squared plus 871.5 squared. And then for the upper bound, I'm going to do the square root again, which is 523.5 squared plus 872.5 squared. So again, using my calculator, I'm just going to write out all the digits on my calculator. So I've got 1016.129175. My upper bound, again, writing all the digits down, I get 1017.501106. As you can see in this last step, I haven't rounded at all. Now, I did this intentionally because this is where we're going to give our answer to an appropriate degree of accuracy. Now, what we need to do here is try and pick a level of rounding here that will give me two answers that are the same. So here, hopefully, you will see that if I round to the nearest centimetre, I get an answer of 116 for the lower bound, but I get an answer of 117 for the upper bound. So this is not right because I don't have the same number. But if I round to the nearest 10 centimetres, I get 1020 centimetres for my lower bound, and I also get 1020 for the upper bound. So my answer here, rounded to the most suitable degree of accuracy, is going to be 1020 centimetres, which is also 10.2 metres, rounded to the nearest 10 centimetres. And again, if you're ever asked to describe why this is rounded to the correct value, then you could just mention that it's the only level of rounding which gives us both the upper and lower bounds equaling each other. Okay, so hopefully that's helped you to understand a little bit more about upper and lower bounds. Again, practice as many questions as you can before your exam on these, because they are a favourite and they're quite hard to spot sometimes, so you're always looking for that bit of rounding in the question there. Okay, also make sure that you know the different solutions to that I've got here in this table, and good luck!